Welcome to our bi-weekly Operate First Community Cloud Meetup. It is again Tuesday and it's again 11 a.m. Eastern Time / New York. We are recording this meeting to give everybody a chance to follow. You can find our privacy policies at op1.st/privacy-policy. This meetup is held under the Open Infra Foundation Code of Conduct, which you can find at op1st/community code of conduct. Look up the details about this meeting at op1.st/meetup. This meetup is a gathering point for practices, projects, lessons learned, help needed and ideas on and around the Operate First idea in general and the Operate First Community Cloud in particular. This meeting can be as interactive as needed, or call it the hands-on meeting. This is the third episode of Season 2, and I'm more than happy to welcome the Kruize project, Kruize Autotune project here in this meeting, led by Rashmi Badagandi, and she will introduce all the others as follows. So, a really warm welcome to Rashmi.
Thanks, Thorsten. Thank you, everyone. So my name is Rashmi. I happen to meet a couple of you guys before in one of the presentations. So I'm the manager for the team Kruize. And I love the introduction that you put up in the community call. It's exactly what we are doing. So we are cruising through the Kubernetes application. So it's Kruize with a K. And I'm joined by my team, my architect, Dinakar, my engineer Saad, and my QE architect Chandrakala. So Chandrakala and Saad would be talking about Kruize HPO, which we are working on deploying on Operate First. So yeah, over to you guys.
Thanks, Rashmi. Saad, can you share your screen?
Yeah, let's do.
Hi, everyone. As Rashmi has already introduced, so I'll just get straight away started. Kruize HPO is one of the projects under Kruize umbrella, so we'll see a lot of projects under it after a little while. So this is the brief agenda, where we would start off with the challenges and performance testing, followed by a brief introduction to Bayesian optimization. And we'll look at the Kruize HPO architecture, and Saad will take us through the HPO demo, and we'll look at some of the experiment results we've had so far. Next slide. Yeah, so imagine you are an SRE and you've been given this task of tuning an application performance. So if we look at any application, we see there are several layers, starting from, if it's a containerized application, you see the container layer, your frameworks, and the runtime layer too. And each of these layers have several tunables. So for example, if we consider the Java runtime itself, it has hundreds of tunables. And there's a warning there, do not touch these knobs, because we don't know tuning one of the tunable, what impact it would have on the other tunables. And given that there are so many tunables, tuning them manually is quite cumbersome. And given that there are so many tunables, choices are never this simple. So let's go to the next slide. Next slide, Saad. So fixing the hyperparameters first. So you must have already heard about this. For example, while building an ML model too, we look at fixing the hyperparameters, because these are the parameters that control the learning process. So here we are applying this for tuning the performance of an application, where we are looking at various tunables at various layers and trying to fix these hyperparameters first. So the various options that we have to fix these hyperparameters are, we could go do a manual search, and we could also we have grid search and random search, but then we have looked at various studies and found that Bayesian optimization better fits here, where we have several tunables, and this would help us arrive at the optimal configuration in a much faster pace when compared to grid search and random search. So this is a brief introduction to Bayesian optimization. So if we look at what is Bayesian optimization all about, so Bayesian optimization is a black box optimization technique where we feed in the objective function that we need to either maximize or minimize. And we also need to feed in all our tunables, which along with the ranges in which they operate. And both these together, they form the search space. So if you look at the graphs there, we see the objective function on the y-axis and all our tunables on the x-axis, which forms the search space. So Bayesian optimization gives us a query point, which is a red dot there, drawn out of this search space. And we use this, each query point there corresponds to a trial config that we apply to the application, conduct the experiments, run our benchmark application, compute the objective function, and then we again go plot it, which are those black points there on the graphs. So as and how we try to, based on the result that we have plotted, Bayesian again looks at the result to predict the next trial config. So it, based on the result that we get, it draws the next sample and gives the next trial config. So using this trial config, again, we conduct the experiment and similarly go and compute the objective function and plot. And Bayesian optimization here uses this acquisition function, the green lines where you see. And in the third graph, you've seen that the moment it has hit the lower point there, it goes back between, draws another sample, which is between the higher 2 points that it has found. And it tries to exploit the area where it is more promising and around the local maximum there. So as in how it has completed exploiting a particular search space, it tries to do exploration. If you look at the fourth graph, it's gone to the further end and given us a new config where it is not very certain about how the outcome would look like. And so on, using this exploitation and exploration techniques, eventually Bayesian arrives at the global maximum. Let's go to the next slide. So this is our Kruize HPO architecture. We've been using this Autotune library, which is a Python implementation of Bayesian algorithm. And these are the various algorithms supported, TPE and TPE multivariate, scikit, and LightGVM. We also have other frameworks like Hyperopt and Dragonfly, which we are yet to explore. So if a user has to use this Kruize HPO, they have to interact with this. We've provided REST APIs to which the user has to provide the search space, which contains the algorithm that needs to be used along with the objective function and the tunables with their upper bounds and lower bounds, or if they're categorical, they can specify that. And once this is fed to the Autotune library, Bayesian returns a config with which the user needs to run the experiment and compute the objective function and give back the result, which is again posted to the Kruize HPO. And based on the result, Autotune again gives us a next config. And this again repeats as we already saw in the Bayesian optimization technique case until we arrive at the best configuration. So we have a small demo here, which will show how to use this Kruize HPO and customize it to any to tune any application. So over to you, Saad.
Yeah, thank you, Chandrakala. So for the demo, let me just start with the repository. Let me show you the repository that we have. It's a group repository, Kruize repository, in which we have multiple projects available. These are the benchmark repo, the actual HPO application repo here, and the UI part that we are working on. So you can see these are the HPO application repo here, and we'll focus on this Kruize demo repo, in which we have created a script in which we run our demo application. So in that we have a a script with which we run the HPO demo application. So to start with demo, what we let me just take you to that point. Yeah. So what we require initially for the demo is we require a search space JSON, which needs to be as an input into this experiment. So let me just one second. Yeah, this is the search space JSON, which contains the experiment name, experiment ID, the trials, and everything. So the experiment is nothing but a set of trials, as you can see, to find the optimal set of tunable values. And the most important part of this is the objective function, which is typically an algebraic expression, which can either be maximized or minimized based on the requirement that you have. You can either maximize the throughput, minimize the cost, minimize the response time, and so on. So then we have this algo, as Chandrakala mentioned in that slide. We have that option of TPA, option on TPA multivariate. We are using the TPA here. And then next, that the important part that comes is the tunable part. So tunables is nothing, can have a can be of bounded values like an upper bound or lower bound with a step, or it can be of a categorical type. So the bounded values can be of an integer or a double with the bounds mentioned with a step value. The step is the important part here, because the step is actually defining the granularity to arrive at that. Let's say if you have to run your upper or lower bound values like to somewhere around 10,000 or so. So your step can be a 0.1 or 1, because that will take a lot of time to run the experiment. So you have to define based on your the upper bound value. You have to define that step as well. Then next comes for this experiment, we are using the Quarkus STC benchmark, and for that we have the tunables that we have defined are the container tunables, Quarkus tunables, and the Java one. So as you can see here, these are the container tunables here, the memory request, the CPU request here, and then we have some Quarkus one, like the third pole or the data sources. These are all the bounded values, and then we have some examples of the categorical type as well, which you can define as a choice. It can be either a Boolean or it can be a set of values. Like here we have defined the garbage collection values for JVM here as a set of multiple choice options there. Next comes is let me just come back to that script that we are running. So like I told you, that search space JSON is the input that you have to provide to that. And then what we are doing is we are reading the search space JSON here, and then we are extracting the experiment name and the total number of trials that are present in that. And then based on that, we are starting our experiment. And here the step one will be to provide that search space along with your this operation. The initial operation would be the trial generate new. So this will start the experiment based on the number of trials. So this T trials is nothing but what we have defined here in our search space JSON, the total trials. So based on that, then this loop will run. Okay, so then comes the next step to generate the config for that for the first trial. So this will hit using the curl command. It will hit that HPO application and it will generate the config. Next, what we'll do is we'll using that config, we will run our benchmark. Our benchmark that, like I already mentioned, we are using the TechMPar Quarkus STC. So we will provide this the config that HPO has given us, and we'll apply that same to the TechMPar benchmark. So what we'll do is here this run benchmark is a separate script that we are running here. I'll not go deep into that because of the lack of time. In summary, what it will do is it will give us the it will apply the load, it will capture the matrix related to that benchmark performance, and it will calculate the objective, the performance objective, and it will give us a value. That value will get in here, and we'll get the status whether it got succeeded or failed. Based on that, we'll proceed accordingly. Then what we'll do is the result that we got back from the benchmark, we'll again send that output to the HPO application again, and that's what it will do is it will again run generate the config based on the result that we got from the benchmark. So this will go on till the number of trials gets completed and we get a final value. So let me just show you once by running it here in a terminal. So So here what we have is we have multiple options to provide the cluster, like it can be a native or a Docker. For this demo, we are using as a native. So by default, we'll take native even if I don't define anything here. So like I mentioned, these are the steps it has to follow. It will first start the service, then the tech empower benchmark that we are using, that will run on Minikube. Okay, then it will optimize, and then the objective value is created, the performance objective. So here, as you can see, it is starting the service here. We have two, like Chandrakala shows in the slide, we have the REST service here and the gRPC one. The total number of trials we are using is 5. So it will start the experiment, and as you can see, it has generated an initial config here based on the tunables that we provided in that search space. So this will gonna take a lot of time here, somewhere around for like, let's say for 5 experiments, I think probably 35-45 minutes will take. So in the interest of time, what I've done is I have taken the logs that we ran earlier, and we can check that and understand how it is going forward. So like I mentioned, it generated the trial config for the here. If you can see for the trial 0, the initial config, it generated this, and then we get this objective function result here. This is the status, whether it got succeeded or failed, and then same with it's sent to the HPO again, and then it generated the config for the next trial. So this will keep going on till the number of trials gets completed. So since we are using 5 trials and we started with 0, so the trial 4 will be the last trial. And as you can see, after this we get our best result out. This is the best parameter, the best value here, the objective function value, and along with that we get the tunables that we defined in that search space. We get the importance as well. Also, this will give us a recommended config at the end, which will have the complete what is the best requirement for it. If you can see here, the best parameter that is generated here, the memory request and the CPU request 3.7, this will be part of this recommended config here. Here. Okay. So along with this, what it does is generates some charts as well to better analyze the output that we are getting. So the first chart that we have here is the hyperparameter importance chart. This gives us the importance of each of the tunables that we have defined in our search space JSON, and their importance value, as you can see. So these are the hyperparameters that are with their importance values. The next chart that we have here is the optimization history plot. The y-axis is having the objective function, the objective function value, and these are the x-axis is the trials. So as you can see, it started with the 0 trial here, and then on the 3rd trial we get the best value here. This is defining our best value. The next chart that we have is a slide chart. It is between the objective function value and the number of trials. What it contains is the individual tunable values, how the importance of those individual values change over the period of 5 trials. So these are the values, and what it is showing here is the darker the shade is, the higher the importance of the tunable. Okay. The next chart that we have is a parallel coordinate plot. The parallel plot contains it is actually showing us the relation between the objective function value and the tunables. So I mean, since we were using a lot of tunables here, somewhere around 31 or 32, so it gets a bit confusing to understand. But later on we'll have a DP part where we can minimize this, and then it will be easier to understand. But in a nutshell, what it is showing here is the dark line here. It's showing the objective function value importance for each of the tunables, whether if it is a categorical one, so the true or false one, that line will show it at what stage that objective function value is having high importance. Okay, and the next is so this is all that gets generated as part of the output. Let me just go back to this. Okay, over to you, Chandrakala.
Yeah, thanks, Saad. So you can see the Genie here. So we usually compare the Bayesian optimization with the Genie because as you see, your wish is my command. So what you ask for is what you get. So if you ask for lower response time, you would get a lower response time, but it could be at an increased cost. So we need to be very careful when we are defining the objective function. Let's move to the next slide. We have some results which we've got by running the Quarkus REST-DC benchmark using 100 trials on a OpenShift cluster. And if we look at the objective function there, we wanted to lower the response time, but at the same time, also have a high throughput and also minimize high tail latencies. So that is the objective function that we have defined, and we fixed the resources here at 4 GB for this run. And the 0th trial gives us the default config, which is at with fixed resources. And there we can see that the default time is 14.21 milliseconds. And with the HPO config, out of the 100 trials, we see around 96 to 97 trial, giving us 2.39 milliseconds, which is like 83% better response time. Let's move to the next slide. Yeah, if we look at the percentages, we got a 83% better response time. And in terms of throughput, we saw 1.3% better throughput here. We also had a collaboration with Kafka team, and they had this Kafka problem where they, given a fixed throughput of 50 Mbps, they wanted to determine the optimal value for these Kafka parameters that would give us the lowest latency, the end-to-end latency. Their objective function was to minimize the end-to-end latency, and they used Kruize HPO for this, and they found that there was a 28% reduction in the end-to-end latency time. Let's move to the next slide. Yeah, these are the repos that we just saw for the Kruize demos and our HPO project, and now we have a Kruize channel too. If you're interested, you could contribute to our project. Yeah, that is all we had for this talk. Yeah, we're open to questions. Thank you.
So this is pretty cool. I'm surprised with 30 parameters that with only 5 trials you were able to get a decent result. Can you give me some insight on how come that works so well?
It was with 100 trials. If we go back to the chart, it was 31 tunables spanning across container, Quarkus, and hotspot VM, and it was 31 tunables, and it was 100 trials there. If you look at the chart.
Okay, so logically, I mean, it would be something like, so each parameter got tuned into 3 values logically, and that's enough. You know, while they're all changing at the same time, that was enough for enough trials to come up with some sort of shape for the surface, right?
Yeah, because the way Bayesian works is based on the previous on the result that is fed in, it gives us the next prediction. So it always predicts based on the result. And yeah, and that's how it was able to predict within 100 trials. But yeah, yes, I think we did give a run with 200 trials too, and we've kind of observed the response time closer to what it was that we got within 100 trials.
I just wanted to add that if you look at the acquisition function graph, Saad, can you please go to that? So the way that Bayesian works is the acquisition function in your presentation. So we, yeah, that one, yeah. So typically Bayesian, explores parts of the search space. So the pink line here is the graph that we are trying to find. So we don't know how the objective function performs. I mean, like, for example, it could be a combination of response time, throughput, and whatever other parameters. So that's the graph that we don't know. That's the black box that we are trying to figure out. And so let's say in this particular case, it's the maximum that we are looking for. The Bayesian starts with some random values, and then it could be on any, it could land on any part of that graph. So once we figure out that, then it starts to figure out, if it's, it's the local maximum or the local minimum. And so it keeps exploring different parts of the search space until it finds the global maximum in this particular case. So it so happens that sometimes, for example, it might find a local maximum, a minimum, in which case, if you see the green graphs there at the bottom, they indicate the acquisition function, which says which is the most, which is the part of the search space which might provide the best values. So that bottoms out at points where it did not find good values, and so it will not search in that part of the search space. Whereas the parts of the search space which were a little bit more promising, it exploits them, as it is called. So it starts exploring newer parts of the search space where it has not looked, and then depending on the results, it continues to exploit them if it finds that they are promising. But if it finds that they are not so promising, then it moves on to a different parts of the search space, and so on. So that's essentially, and of course, all the different algorithms that we were looking at, I mean, TP multivariate, and so on, they have different efficacies in terms of how quickly they can arrive at the right values. Yeah, of course, there's nothing that can arrive within 5 trials. It will take a pretty long time. But there are a few of them which we have not explored really, like things like XGBoost and so on, that do actually shorten the amount of time that it takes for you to arrive at the the best possible values, essentially.
If you go back to the chart where it had all the trials on the bottom, and then the score was near the end of the slideshow.
The slides.
Okay.
That keep going. Nope. Way at the end. That one, probably, yeah. So it looks like every once in a while it goes, does like 5 or 10 that are looking at the local minimum, but then it does a jump. Is that part of the algorithm?
Yeah, that's the exploring versus exploitation that I was talking about. So the
Okay.
exploration, so the ones where you see values, so here lower is better in this particular graph. Can you hit on slideshow, Saad, so it will be easier for?
Yeah.
So the values lower are better, and so when it tries to explore a newer part of the search space, so that's when it finds that the response time goes up, because it may find something that's not so good. Then it starts to look adjacent to that, and then find something that is good and starts exploiting that. So that's why typically it does something like around within, let's say, if you consider 10 trials, around the first 2 or 3 of them would be the exploration part, and then comes the exploitation part. And so that sort of repeats all through the 100 trials that you see there.
Thank you.